And this is today's task. Okay, the bells are ringing, so it should be 11. 1 minute is on. Okay. In the meantime, do you have any question about the last topic that was about magnitude? What about your homework? Are you there?
Yeah.
Okay. So you cannot invoke the fact that you're not listening to me.
Yes.
So
I tried to watch the video. I went to YouTube, but it has not been uploaded yet.
Well, actually, what I'm the homework was a simple reading, and okay, about the topic, you can go much deeper than we did about the use of long period signals to better assess what, in principle, is MW. You know that, well, now you should know that the original definition of magnitude was an instrumental one, later known as ML, connected to the local conditions in California and to a specific instrument. So later we discovered with the expression, the logarithm of A over T, and T was referring to different periods for body and surface waves, and the limit, and their limit, that was saturation. And saturation is connected to what we call the source spectrum. In the sense that, okay, we can go longer periods, shorter frequencies, but sooner or later we reach the roof of the maximum of radiation unless we go to very long periods. That's the idea of MW. So to use M0 as an estimate of the energy to be intended to a magnitude definition. And that is clean and, let's say, easy in theory, but in practice, how to estimate M0. Because on a routine basis, magnitude assessment should be released as soon as possible. Let's say after minutes, after tens of minutes, after 1 hour of an event. Now, it's not easy to collect long period data in such a relatively short time. We can collect long period surface waves like, okay, let's say 100 seconds if we use global seismology, but please remember that we need, let's say, 1 hour and a half for the waves to reach the instruments on a global scale. Okay, by the way, processing hundreds of seconds for mega events, it could be not sufficient. And that is why longer periods are invoked, like the three modes of the Earth. And this was the idea of Stein and Ockel to better assess the magnitude, for example, for the Sumatra event. So S02 means, okay, to go to very long periods, 54 minutes. Can we use something longer in the sense of periods? Well, the answer potentially is yes. There are two ways. One is to use the longest period that we can imagine. So, for example, infinite periods. One example is the near field motion, because the static displacement, let's call it the near field or fling as engineers call it, okay, that is left forever. So a static displacement has an infinite period. The problem is that we need a measurement around the fault because it's near field. So GPS, but in many cases we don't have GPS very near to the fault. The other possibility is to use the three modes of the Earth, but we need some time to record and to process them. Or, but it's too late, tsunami waves, as we will see on web, because they are long period kind of motion induced by earthquake. So that was the idea of a paper, of a tiny paper that was your homework. I hope that this sequence of logic steps is fine with you. Is it?
Yes.
Yes, yes.
The logic is important. Okay, good.
Yes.
Because for today, we will make another detour and we will try to speak in 1 hour and a half about an elasticity that is a very general and broad topic. Or we can call it also attenuation, that is going to cause some nice consequences in the estimation of what we can call the Q of the Earth. So we will start very briefly with and I will be very quick, as a sort of a recap of what is intended to be an perfectly elastic rheology. Then we will rediscover a non-Hookean rheology, and we can call it Newtonian rheology, but that is valid for fluids. And so you could say, wow, that's a fluid. Yes, but we're going to use some viscose powder to be added to the elastic rheology to create a model, and we will call it SLS, as it is written here, standard linear solid, where we're going to further generalize what we can call Hooke's law. So we will create a model, and then we will try to apply that model to the Earth in general, and then to get a couple of ideas about the consequences on the wave field propagation inside the Earth. And this, we will discover that what we call velocities, seismic velocities, they will become complex. And we will get, as a final surprise, also a sort of a dispersion, but it is not the dispersion of surface waves, it will be the dispersion due to causality and anelasticity. So this is today's recap. If I'm able not to make this whiteboard to collapse on my head, let's take just as an example, and this is the message to take home today. Now let's take a general definition of velocity. Could be P velocity, could be S velocity. Okay, let's take Vs, for example. Okay, let me unshare my screen just for 1 second so you can see better the, maybe the blackboard here. If you take this velocity here, and it's the standard one, it's given by a ratio of an elastic modulus, in this case a rigidity modulus, divided by some inertial properties, but of course they are related to density. As you see here, that's a tiny and clean definition. And the key is here in the mu, that is a generalization, if you want, of Hooke's law. Hooke's is relating force and displacement, but when it is generalized, it's relating stress and strain. Okay, and that's Hooke's law. There is no time there. There is no time for the system neither to relax or to unrelax. Everything is immediate, takes no time. You apply force, you get a displacement or stress and strain, and vice versa. And when you remove the stress, immediately the system is going back to the initial condition. That's Hooke. There is no time there. And you can imagine that mu, the ratio between stress and strain, is a real as it should be, value. It has its units, whatever. Now, for a system to have time to relax or to unrelax, we need to add some viscose powder here to create a sort of a viscoelastic rheological model. But just using intuition, the only way for a number to take care about time, if you think about it, is to move from the real domain to the complex domain. So if you have amplitude and phase in a number, in a complex number, you have the amplitude and you have the phase that is taking care about the time. So the message to take home here is that the elastic moduli will become viscoelastic moduli, and they will be moving from a real domain to a complex one. And if this is going to happen, also velocities will become complex. And if a velocity is complex, now I'm getting really hazardous now, and that will be the last topic, hazard. Okay, now, when you write a typical wave that is propagating in some direction with a wave number k, if velocity is complex, k will become complex. And if it is complex, okay, then we will have the real part that is going to be propagating, the propagating factor, but the imaginary part will be the damping in the propagation part. That's the idea. And that's the only idea that is necessary for you to take home. That will be necessary, but not sufficient for the exam, of course, because for the exam, you will need to know also what we're going to discuss today. But that's the idea. Moving from Hooke to viscoelastic domain, complex moduli, complex velocity, complex case, and we have a propagation and attenuation factor. That's it. Okay, let me share again my screen, and let's go quickly through the first slides. Okay, this is summarizing what I was telling you. Okay, Hooke's law, stress and strain, no time dependency there. If we want to add some time-dependent behavior, we have to move to the unelastic domain, or you can call it viscoelastic behavior. Now, to do that, how we can generalize our simple, but it's really nice, but simple Hookean rheology. Well, we have to move from a simple, relatively simple concept of strain as a measure of deformation from solids, real solids, Hookean solids, where you apply a shear stress, for example, you move it, you have an immediate reaction, like for example, connected to mu, to the rigidity modulus, but then you're not making the system to flow. If you remove it, it's going back to the origin. That's the essence of mu. But if you take a fluid, if you imagine now to have two plates, typical viscous, Newtonian viscous behavior, you apply a shear stress, you are going to get a reaction. Well, for an ideal fluid, there is no reaction because mu is 0 and the fluid is standing, but that's the ideal fluid. Feynman was calling this as a dry water, just to express this paradox. But for a more realistic, and we can call it viscous fluid, when we apply a shear, part of the fluid will flow. And it's going to create a profile along the fluid. And if that profile is a slope, a linear slope, it's called a Newtonian fluid. So traditionally in seismology, fluids are considered to be pure fluids, ideal fluids with no shear resistance, and they are called inviscid or Pascalian fluids. But more realistic fluids, and there is a huge family of fluids, you can also study polymers there. But of course, the simplest viscose rheological model is the Newtonian one. In the Newtonian one, we have a deformation rate. That's the key. And if we have a rate, we have a time factor there. So just developing this idea here, and if you imagine now to measure a shear, and if you want to imagine a shear strain, you imagine the delta x with which you're pulling your fluid, you consider the height of the fluid, and you consider the strain inside the fluid. So you take this, and if you compute the shear rate, and now that's the key, this dot here is the key. And if you compute the time derivative of this quantity here, you get something that is telling you that the shear strain rate in a viscous fluid is decided by the slope of velocity. You know that moving from seismology to fluid dynamics, the motion, how to say, the equations of motion are changing from the, okay, you can use continuity equation, you can develop the dynamic equations, but instead of being the elastic equations, like for seismology, you're going to build the Navier-Stokes equation, for example, in fluid dynamics. And for those equations, the key quantity is no more the displacement, but it is velocity. And the velocity profile that you're going to create when you're pulling a viscous fluid is deciding its history. So we're moving from displacement to velocity and from shear strain to shear strain rate. And that's the time factor that we will need later. So the typical example of this shear flow in a fluid that is not an ideal fluid. Ideal fluid will not move. You're not going to generate nothing there. But in a what we're going to call a Newtonian fluid, the profile that we're going to generate is a line whose slope is decided by one additional property that is called viscosity. So if the slope is constant and you have the maximum velocity here that is corresponding to the velocity with which you are pulling the first plate, and going to zero here because that's a boundary plate and it's fixed, you cannot move it. And if you're going to generate a profile like that, okay, the fluid is called a Newtonian fluid. And the slope is decided by this, and this is called viscosity. So there is another extreme rheology, a simple one, but is traditionally used in fluid dynamics, Newtonian fluids. Now you take here the shearing stress and not the strain, but the strain rate, and that's a line. So it's again a simple plot, like the Hooke's plot, but instead of having stress and strain, we have stress and strain rate. So that's the dot there. And now this quantity here is keeping time inside it because its units are Pascal per seconds or Poiseuille, as you want. Okay, that's viscosity, and that's an ideal but Newtonian fluid. So we have Hooke, we have Newton. In their life, they compete. They competed for a long time. Now they are belonging to two different rheologies. We're going to mix them, adding some Newtonian powder to the Hookean fluids. Now, just a few words here, because we're going to use just this. But please remember that when you're going to dive inside fluid dynamics, and that is not my cup of tea, you can go deeper with things here. You can have an idea with which are the parameters that are deciding, for example, viscosity. And the key parameters that sometimes, well, usually in seismology, they are neglected, but they are there because temperature and pressure, they decide also how a solid will behave in time. And that is one of the ideas that you will discuss also with Karim, or maybe you are discussing with Alessandra. But going on a little bit more detailed view of viscosity, well, it depends on temperature and pressure, and of course on how to say, microscopic properties, or let's say rheological properties like activation energy for the flow, because if you don't overcome it, nothing is going to flow. Material property is something like that. Just to remember you that what we're going to use today is a simple rheological version of a rheology that could get very complex. For example, you can study other than simply linear rheologies when you consider shear stress and strain rate. We are going to use a Newtonian one today. The ideal, no reaction, but you can have plastic behavior, and so you get a reaction only when you overcome what is called yield stress. So nothing is happening, then you're overcoming, and then you're going to be plastic. You can mix them, you can call them pseudoplastic. And so there is a word there of different rheological animals. Again, we're just to use this, but remember that you can generalize them, and you can get some very nice rheologies that are typically studied in material science. This is not, we are going to stay here, Newtonian. But remember, you may have a shear thinning, you may have Bingham plastic, Asson plastic, whatever. You can study ketchup or mayonnaise or whatever. We are just going to consider these ones. But remember that there are many ways to generalize them. And so this, the relation between shear stress and strain rate can offer you a large variety of things here. But okay, what is our topic for today is trying to understand, well, actually, in principle, our topic for today would be to understand the rheology of rocks. But we will, and this is what we're going to do, but actually in this course, what we're going to consider is just a model to understand anelasticity during wave propagation. But rock mechanics, as you're going to explore in the Karim's course, can also consider other time scales. For example, you can consider very long time scales, maybe geological time scales, or let's say thousands of years, hundreds of years. Actually, our time scales in this lecture, at the end of the story, they will be relatively short. So the time scale of wave propagation inside the Earth, and knowing elastic seismic velocities, we know that it's a matter of seconds, minutes, hours, maybe some days for the three modes of the Earth, but that's short. Another topic, and very interesting topic, could be to understand how rocks behave in specific temperature and pressure regimes on very long times. And so let me have here a couple of words that you're going to use not only today with me, but also in Karim's course. And so generally to study what is the strain inside the rock, a real rock, in time, and now you see here, we don't have to imagine seconds, minutes, or hours, but maybe years and millions of years, whatever. So you have a regime where you apply a stress, you get the strain, that's the elastic if you want. You can call it transient. Okay, you're going to shear. If the stress is not that much, it's going back to the equilibrium, okay. But then what happens later is that, okay, there is a slowing of this creep. And in any case, strain is going to be accumulated with a linear fashion in time. then you may have accelerated creep. But the only word that I want to stress, to highlight here is creep. And creep is a general word that is, trying to describe how something is going to deform in time. Okay. So again, I'm opening windows here on other courses, because then of all these open windows here, we are going to take just one, trying to understand the Q of the Earth in terms of wave propagation. Let's keep that in mind. Now, what is happening when you remove a stress? So you apply, you remove. Okay, in the typical Hookean behavior, it's going back to the equilibrium in no time. But when you consider a real creep curve, you go beyond over a limit and you're not going back to the equilibrium. And if you remove it, it's going to be permanently deformed. And in some cases, if you overcome some limits, of course, you can break them. So you may have a fracture at the end of the story. You may have something that is left there as a permanent strain, so energy has been accumulated by the system, and so on. Remember that the elastic, the typical seismological approach is just elastic. But to understand also to how these systems can evolve in different time scales, not only the ones that we're going to explore today, we have to consider a rheology that is a sort of a mixture of an elastic, purely elastic, hooks, solids, purely viscous, Newton, fluids, and we will try to put them together just to create a model that is going to be able to describe all these features here. But again, we will explore just a part of them, but remember that the same concepts will be applied to you also for other rock mechanics problems. Okay, so the broad frame where we're going to move today is to consider viscoelastic domains. What does it mean? Okay, we have to mix solids and fluids. So all these slides here are just a sort of a recap and just saying that you are going to mix them. Again, if you want to classify typical materials, for example, if you apply a force to a solid, maybe you have a totally rigid one. It's like diamond, I don't know, something like that. So you have no deformation. You can do whatever, no deformation. But of course, that's not interesting to us because we want to understand how this table, my table here, is reacting when you apply some perturbation, a short time perturbation, like a delta for its function. And so the typical domain is the Hookean one, stress, strain, linear. And here you have an elastic modulus. What about fluids? Okay, in many cases, solid people is saying, no, they are inviscid or Pascalian. If you apply a shear stress, no reaction. So mu is 0, fine. In other domains, okay, you have linear viscous, Newtonian, but please remember that you may have other nice, but unknown to me, rheology is much more complicated than non-linear ones. Again, what we want to do today is consider viscoelasticity in order to explain the attenuation of a seismic waves in the Earth. But at the same token, please collect some terminology here that you can use also on much longer time scales. And to conclude this easy but potentially complicated introduction here, let me simply recall one of the original definitions of rheology that is a relatively young but exploding branch, and it's about the study of the deformation of materials when you apply stress. And we have a huge variety of materials that we can consider. And so one of the Reiner, that was one of the founders of, in the 60s, of rheology, for example, he defined using this short text from a holy book, the Deborah number. The idea is to consider rheologies considering, okay, the time that you are devoting to observe your system and the time necessary for that system to relax. So to go to the equilibrium. You may have two extremes again. For example, typically in a solid, you knock, if you are a seismologist, okay, you consider perturbation. And the time of observation, that is hours compared to the rheology of millions of years, is going to infinite. That's one example. The other extreme is when a fluid takes pretty much no time to relax because it's flowing. So it's going to zero. We have many words inside this from infinite to zero times, and that's you can take many ways there to study different rheologies. So in general, we are coming from a solid-like response, trying to get some of the fluid's behavior to discover some rheological features of materials, which ones, in our case, the solid rocks. Okay. Of course, if you're studying the outer core, you can apply simply the liquid-like response because it's pretty much a sort of an ideal fluid. But today is okay topic to understand an elasticity. Again, please try to broaden your perspective because rheology is much more, how to say, broad. Okay, let's start now. And what we're going to build is starting from the two simplest elements of rheology. And the first one is this one. It's elastic, it's a spring. Okay, it seems a resistor, but that's the Hookean piece of the system. Easy, stress, strain, and we have an elastic modulus. In this case, I'm calling it G. Good, we know it. Now, and that's the first. Let's imagine now to consider two experiments to be applied to this system here. For example, the first one is, okay, we apply a stress and we study the strain. So we take it in the equilibrium, we apply a stress, and we study the strain. You can answer it immediately. Okay, but immediately, and it's responding immediately. By the way, we will call this as creep experiment. New word, new name for something that is very simple for us. On the other way, what we can do is, okay, let's apply a deformation and let's study how the stress is evolving. That is called stress relaxation. And for this element here, it's so simple. It's so simple that it's not very interesting for rheology here. So for example, you take a material, you apply at a given time a strain of a given amount. In no time, immediately you get a stress. How much? Well, it's G times this. Good. On the other side, if we apply a strain, or pardon, a stress here, and we measure the strain, okay, if we apply a stress for a given amount of time, like this boxcar, nothing, okay, we apply, then we remove it, we immediately get a deformation, a strain, this amount, we remove it, everything is immediate. And that's fine. Okay, no news here. Let's consider the other one. Now a pure viscose. Okay, I don't know it very well, but you know, because you took some fluid dynamics courses and you know that Newtonian fluids are considered to be the simplest, one of the simplest fluid classes here. Well, the symbol for this element here is the dashpot. Actually, we used this for the harmonic oscillator when we damp it. Damping is typically represented by this system. That's why in the harmonic oscillator dynamic equation that I've been writing also with you, there is a term related to the damping forces that is proportional to velocity. Okay, that's its origin. Okay, you assume that the vibration is occurring in a Newtonian fluid. Good. Stress is related to strain rate, and it's decided by viscosity. Can we imagine to apply the two simple experiments as before? Okay. If we apply now a strain, immediately, no time is going to develop a stress there, but just at the time of its derivative. So here it's acting as a stress. So you have a sort of a delta-like response. And then nothing. And what about the creep? Well, if you apply a stress, now you take your plate and you move it for a given amount of time, okay, now the strain is increasing. It's increasing. How much? Well, it depends on viscosity. And then it's going to stand if you stop. But here, the dislocation, also if it is not the proper word for fluids, but the flow has taken time. The fluid is not going back. It's going to stand in the new equilibrium position. How far is it from the initial one? Well, it depends on viscosity. You can imagine two extremes here, I don't know, but an infinitely viscous fluid, okay, you're not going to develop, and the flow is going to increase in a very slow fashion. If viscosity is zero, okay, well, it's coming to you immediately. Of course, these are two extremes. By the way, here we understand that the amount of strain is decided by viscosity and by the amount of time that, along with, we have applied the stress. Okay, these are the two basic elements, and usually they're treated to be separated. I don't know, seismology, fluid dynamics. Now we're going to create, in the next slides, some starting from the simplest and going to be simplest but most interesting to us model that we're going to use to understand the Q on the Earth. Now a word, let me make a 1 minute pause here. Stop sharing because I want to see you. Up to now is just a recap with some new words, maybe rheology, something like that, of what of something that you know, that we know. From now on, things are going to be a little bit more algebraic from a point of view, because we are going to write some answers of the rheological networks that we are going to build. And my and our purpose here is to build what we're going to call standard linear solid. I will be very quick. And as usual, you will see some expressions here, algebraic expressions or formulas or time histories that we don't have to know piece by piece, but we have just to understand them. So my usual warning here, there could be some slides full of beautiful formulas. Please, my purpose here is just to understand the logic. Is it clear? Okay.
Yes,
It
yes.
is.
Okay, so let's try to start and to write these time histories. Let me share it again, and let's build them. Now we're going to build networks like this. We can call them viscoelastic modeling. And we will consider first the two simplest examples where we're going to mix those two elements in series or in parallel. We will get their responses, their creep functions, if you want. It will not be enough. Then we're going to build what I will call the Zener's implementation of this, of a standard linear solid. Then you will see the general expressions of a standard linear solid. The idea is just to get a new constitutive relationship that will allow us to consider an elasticity in the Earth. And at the same token, you can use them also to understand behavior of systems on long times. Now, if we put this system in series, we will get the Maxwell element. If we put them in parallel, we will have the Kelvin-Voigt element. It will not be enough. But again, let's try not to get lost in algebra. Just use intuition here. If we take a series element and we apply a stress, okay, the deformation will be the sum of the two. Okay, that's easy. But the stress applied at the two extremes, at the two arms of the elements will be the same. On the other side, if we take a parallel element, the stress will be the sum of the two branches, but the deformation has to be the same. And at the same time, let's remember also in some extreme cases. For example, if you put here a system that is undeformable, you can apply whatever, it's not going to move. Vice versa, like for example, infinite viscosity. Or if you put there something that has no viscosity, you take it and it's going to break. So these are the two extremes. Okay, let's try. Now I'm going to be a little more quick, but again, please don't concentrate on algebraic details, but just at the final answer. Now let's imagine now to build what is called the Maxwell model. Now we have a spring, we know it, we have a dashpot, okay. We will call in general, the relaxation modulus, what's going to happen in time. Why time? Well, because the spring is going to act immediately, it will react immediately, but then the dashpot will act with a delay that depends upon its viscosity. Okay, now let's try to deform. Now the strain will be the sum of the two strains. And since we have to deal with strain rates, the strain rate will be the sum of the two strain rates. Okay, good. We know the rheologies, we know this, we can write it, but it's dynamic equation if you want. We can rearrange it and we can write it like that. Now wait a second, because what we can call here lambda is the ratio between a viscosity and an elastic modulus. You see, they're going to mix now. And by units analysis, it's a time. Well, it's the time needed for the system to relax. Now you can imagine if this dashpot has no viscosity, it will react immediately and with nothing. You're going to wipe out the spring. But if it is infinitely viscose, okay, this is going to be stuck there and you're just going to move a spring. So eta here is going to decide what is the importance of this. And actually, if you're going to study to solve this simple dynamic equation here, one of the first answers that we can get is that, okay, if we apply a strain like this one, like a step, okay, the spring is going to act immediately and you have that instantaneous deformation. How much? Well, it depends on the elastic modulus, of course. And then the other side with the dashpot is going to relax. And okay, it's going to absorb all the deformation and the stress there is going to relax with a decaying time that is related to lambda. Okay, if you imagine now to put an infinite viscosity there, well, that piece is never going to move, and you will get just the elastic behavior, but no news there. So you see that this lambda is deciding, it is the ratio between G and eta. It's going to decide how the system will evolve in time. Good. What about the creep? Now we take the same equation there and we study what's going to happen if we apply a stress there and we study the deformation. Okay, now we will have an immediate, no time response by the spring. Then the dashpot is going to deform. How much? Well, it depends on viscosity, of course. If viscosity is infinite, well, this is going to be nothing. But then we remove a stress here. Okay, the spring will relax immediately, but we will have a permanent set there due to the fact that the dashpot is going to be relaxed in some way. So the deformation is going to be the sum of its two elements. This will depend on the time and on viscosity. And now we can imagine to make a sort of a ratio of the general stress applied and the deformation that we get at the end. Okay. And you can imagine that the ratio between stress and strain in this case is going to be this. Now, so this is the modulus, the first viscoelastic modulus that is relating stress and strain. Again, a check here. If eta is infinite, this will be just the elastic part. If it is zero, the system is going to explode because it will come with you. If eta is something, well, it will decide the time and so the permanent set to be left. Good, that's Maxwell. Is it fine? Is it nice? Yes, but it's not enough. Because if you compare the creep and the relaxation that we're going to get, this is the summary of it. But for a real material, that's not the case. Relaxation is fine. Still, we have this detail here to work it out. And here, we don't have this recovery that is left there forever because it's going to relax again. So it's nice, but it's not enough. Can we check another simple model? Okay, let's call it the Kelvin-Boyd or Kelvin. Now let's consider a parallel. Okay, now the stress is the sum of them, not the deformation. So its dynamic equation is this one. And now you can imagine to put this as an extreme. Okay, if that is going to be zero, again, that arm is not going to, that branch is not going to work. If it is infinite, well, nothing is going to work. You cannot move it. Let's check, at least for one case here. Let's consider the creep experiment. What's going to happen here? Okay, if we switch on the stress for a given time, that is until 2Ts, the deformation is going to be built. It's trying to reach the elastic one, but it is mediated by the viscosity there. So the growth to the final deformation is decided by viscosity. And if viscosity is infinite, you will never let the spring to act. So this is going to retard the time needed for the spring that would like to act immediately to react. So the deformation takes some time to reach its final limit, and the time is decided by lambda. And lambda is again the ratio between G and viscosity. Then if you move the stress, the spring would go back nicely to the equilibrium immediately, but now wait a second, because you have a decay also here due to the fact that the dashpot is acting. Oh, that's interesting. But on the other side, if we study the stress or relaxation, if we apply now a deformation, well, the stress on the spring branch, it will be the elastic one, but the dashpot will act just at the beginning because it's proportional to the strain rate. So just at the beginning, it will be a delta. So that is nice, but not so nice. So we are getting something interesting on the creep part, but on the stress, we are weak. And actually, if you take the Kelvin, okay, we're getting something here, but here, that's not nice. So these two simple systems are not enough to describe what we want. Okay, what is the simplest rheological model that is going near to what we want? Well, it's called standard linear solid, I'm sorry. And there are many implementations of it. We will take the simplest one, which is this one. It's called the Zinner's model. Now, again, in the next slides, you will see many formulas to appear. Just use the logic. Okay, let's take this example. Now we have a Kelvin on the left, now in series with a spring. This kind of implementation is called the Zener's one. By the way, what we're getting here? Well, let's imagine now, before looking at the equations, what's going to happen if we apply a stress? Well, G2 will react immediately, while G1 will be delayed by eta there. If eta is nothing, well, it's just to have two springs in series. Good. If eta is infinite, okay, only G2 will be left. By the way, looking at the branches, now the deformation will be the sum of them, and gamma 1 is decided also by eta, and the stress will be the same at these two branches, and here is going to be decided by eta. Now, if you put the things together, you get this. Now, and this is the message to take home. A standard linear solid is the simplest rheological model where we have now all the terms. What do I mean here is that we have stress, strain, and stress rate and strain rate. Please do remember that for Hookean typical rheologists, we have no time. And actually, it's this one, this and this. On the other side, the viscose element will appear in the rates, and here they are. Now, I'm going to say this again also in a couple of slides, but let's try just to use intuition here. Let's imagine that we're forcing this system at very high frequencies. Now, with very high frequencies, with very high frequency forcings, the derivatives will take the leading role. So this and this. On the other side, if we're going to excite this system with very long, relaxing actions, the time derivatives will not act, and this part will act. What is the meaning here? That according to the frequency of the excitation, this system will have different behaviors. And this is what will emerge in a couple of slides, and we will call relaxed domain and unrelaxed domain. This is just an anticipation. By the way, a standard linear solid is characterized by the presence of stress, strain, stress rate, strain rate. So all the four elements. What are one of the consequences? Of course, the first one is that algebra is getting more complicated here. Because if you're going to study here, for example, the creep function, that is one of the most important ones. Now let's imagine to consider the initial state. Now we apply here a stress. This will give an instantaneous response, and then the final state will accommodate also the contribution from the dash belt. Okay, if you consider these terms here, you will see that we have an instantaneous response from G2 here. How much? Well, it depends on G2. That's fine. Then the other element will enter into the game. How fast? Well, it depends on eta. And sooner or later, if we leave a stress there, okay, also the elastic part from G1 will enter. Now look at this plot. We have an instantaneous response, and this is ruled by G2, and a long time response, and this is ruled by G2 and G1. And they are summing as the reciprocals. It's like electronic circuits. Now you see, I hope, what I was meaning. We have a response on short times and a response on long times, and the transition is decided by eta here. Okay. Main message for the second part of the lecture, because now, if we want to define what is in general the ratio between stress and the general viscoelastic moduli, and we can call it the creep function, we can rearrange it, we got this. And we have a time that is related to the viscosity over G1, and it's averaging the effect of G2 and G1. On the other side, if we want to study to write the stress as a function of strain by a given moduli, so tau dt of t is a function of the deformation of t, that is the general stress, or if you want the modulus that you can write. And now you see it's made by different terms, and everything will depend by eta. So eta is a sort of a messenger, a time messenger that is deciding the reaction on short time scales and the reaction on long time scales. And now, if we're going to compare the result of a standard linear solid with something that is near to the behavior of rocks in time, what we see is that what we can call the creep compliance, so the response, for example, to stress, is going to move from an immediate response, and we can call it unrelaxed, to a long time response, and we can call it relaxed. And you see that they are different. So they behave differently at different time scales. At the same time, the relaxation modulus is going from an unrelaxed, the first spring, to a relaxed at infinite time. That's the key concept of a standard linear solid that, in its general fashion, can be written like that. So this is the general writing of a standard linear solid. Now, let me add a few words, and then we will take a 1-minute break before moving to the, let's say, the final part of the lecture. Because the constitutive relationship of an SLS in general is made by a stress and a strain. And that's fine, it's like hooks, stress, strain, and then a modulus. But now we have also something that is dependent upon the stress rate and something about the strain rate. And to balance here the units, the quantities that stand in front, they have to be times, of course. These are called characteristic relaxation time. And you can imagine that this is going to tell you the story of strain when you apply a stress, if you want the creep. And this is going to tell you the story of stress when you apply a strain, if you want, that's the relaxation experiment. Now, what about this R here? Well, let's imagine that we wait for long, long times, or if we have perturbations that are so long in time where the derivatives are not active, no more active. Okay, these terms will drop, and what is left is this, stress, strain, and a modulus. It's called relaxed. But on the other side, if now we're going to shake it very rapidly at short time scales, well, the derivatives will take the leading role, and actually we're going to have stress and strain, but related by MR times this, well, 1 over, you will see the expression there. And the equivalent viscoelastic modulus at short time scale will be different, and that will be called unrelaxed. And for your joy, I know it's not a joy, it is not a joy for you, it is not a joy for me to write this slide here, but now we can summarize the standard linear solid in general, because if you're going to open a rheology textbook, maybe you're going to look for the creeps function. And the creeps function usually is written like that. So you have a deformation in time that is made by an instantaneous response, and you see this is unrelaxed, plus its time evolution. That is called the creeps function. And an expression like this, from the first expression that you've seen there, can be written from that equation also like that. You see this ratio here. And the Zinner's example that we discussed a few minutes ago, it's just one case here. So you can rewrite this in terms of this. Now, what are we doing here? Well, actually, what we are doing here is just to generalize the Hooke's constitutive law, adding some viscose part that is revealed in tau sigma and tau epsilon, that is telling us, okay, now the old elastic material, you can imagine that it is the unrelaxed response. And mu, for example, for S waves and P waves is our classical one. But for unelastic materials, the viscose property can change it. And you may have a relaxed modulus that is made by mu times vis2. And the creep function is written like that. Of course, if you switch off the viscose part, everything is going to collapse back again. Mr and mu are the same, and this is 0. So we generalized, for now, the standard, the Hookean rheology. We took a little bit of Newton, a little bit, it depends, but a Newtonian one, we added it, we built a standard linear solid, and now we have time inside. And we generalized the constitutive relation from stress and strain, including the time derivatives. Up to now, nothing is about seismology here. No, let me add one other, the most terrible one, then we will make a 1-minute pause. Because the end of the story actually, and it could be an important one, is that now, if you want to define the general ratio between stress and strain, well, the answer, my friends, is blowing in the complex numbers. Because, and this is the algebra that I'm skipping, if you want to write in general sigma of t over the strain of t, now you can write an m star, and you can call it viscoelastic modulus, where you have a real part plus another part plus an imaginary part that can be written like that. Wait a second, because if mu is equal to mr, this will be 0, this will be 0, and everything will go back to the origin. But if we have some viscous effects there, mu is different than mr, we have a tau sigma that can be written also in terms of tau epsilon, and we have this with an imaginary part. And the velocity of information propagation in that system there, in terms of its modulus, can be written like that. Now, a velocity square usually is a modulus over density. I was writing this on the whiteboard at the beginning, and that is fine. But here we have an additional term that is there if we have some viscose parts into the game. And it depends upon frequency. Because if you're shaking your system at high omega or low omega, you will have different behaviors. And then, if you define what is called the Q of a system, so the quality factor of a system, it will have this expression. Now, 1 minute's pause before going to the last step. Stop sharing. Okay. What have we done until now? Well, we called new rheologies, we invoked some Newtonian, we created some viscoelastic. Why viscoelastic? Because there is a spring and a dashpot. And we created some viscoelastic circuits. Maxwell, Kelvin Voigt, very nice, but they don't fit to our needs. Standard linear solid, stress, strain, stress derivative, strain derivative, and we found different behavior at different times. Question. When I was teaching the wave physics course, when my courses at the university were less in number, a part of it was about the definition, just one slide, of Q for a system. Question number 1 for the diploma, guys. Have you defined the Q in the wave physics course?
No.
No?
Yeah.
Oh. Not so good to know. Maria Aurora, do you know what is Q?
Yes, it's a quality factors that define the amplitude loss of the seismic wave when they propagate through the earth.
No, that's the end of the story. That's the end of the story.
Well, quality
The
factor.
beginning.
All right.
The beginning of a story.
Well, in terms of quality, sorry, Professor?
In terms of quality for an oscillator.
For oscillator, well, I properly studied Q factor in the exploration and applied a master degree at the University of Pisa, Seismology, where we study the part of geometrical spreading and dissipation as well. Then in rock physics course, we study Q factor by my own.
Okay. Yes. Okay, guys. Okay. We're going to spend 5 minutes in a recap here because it's otherwise we're going to get lost. Okay. Okay. Wait a second.
Yeah, because I think that for instance, in my courses, I have studied quality factor in terms of, yeah, the amplitudes and the loss parameters. Yeah.
Okay. Well, definition of Q is very simple, very simple. Now, let me spend 5 minutes on this, because otherwise we don't understand what we're looking for. That will be the Q of the Earth, Q for an elasticity and stuff like that. Now, let me share my screen. Okay. Do you see it? Hello?
Yes.
Yes.
Okay. You see, this is theoretical seismology, okay? Now, somewhere here, there should be my other courses. Where are they? Huh. Okay. I hope it's still there. Okay, I was passing this to Lapobowski, so I was thinking that he was using this. Okay, these are the PDF of my old course, that is the beginner's course, okay? And Maria Aurora have something similar for a course at the university, okay? But by the way, now look at this. This is about force and damped. Let's see if it is working. Okay, you see, this is very simple, very basic. It's one of the first lectures for the diploma course. Do you see it?
Yes.
Okay, look. Very simple pictures here. The writing of the harmonic oscillator with damping. And B here is exactly viscosity, okay? You write it, initial conditions, weak damping, strong damping, critical damping. That's important for engineering geology because, okay, I will say a few words on Friday, but one of the most important things used in engineering seismology is what is called response spectrum, and the response spectrum is considered to be at 5% of damping, and that means 5% of critical damping. By the way, this is damping. This is the energy of a damped oscillator. Now, in a damped oscillator, energy, of course, is not constant. I mean, for the spring and the mass. Why? Because amplitude is diminishing, of course. So it's no more the complete game between potential and kinetic, kinetic. So hooks and velocity. No, because part of it is removed and it's going to increase the temperature from on a microscopic scale of the Newtonian fluid in the dashpot. But what does it mean? That energy in a damped oscillator is going to diminish with this rate. I'm sure that you did this, right?
Yes.
And if you, okay. Let's imagine that you hadn't, then you can find the slides here. Now, let's define the quality factor of a damped oscillator. A damped oscillator that now has 3 parameters. It's the mass, is the spring, the constant of a spring that is entering into omega 0, and B, that is the damping. Now, if you take the ratio between omega 0, its natural frequency, and the damping, you get a pure number, because this is 1 over time and this is 1 over time. It's a pure number. And if you're going to compute the fractional energy that you lose every cycle in a damped oscillator, and you develop this, that's the square of the amplitude, that's the initial amplitude, and if you take the time derivative, you get this. So the Q factor that is defined by the ratio of the natural frequency over the viscosity actually has also the meaning of being 1 over exactly. It's telling you how much energy as a percentage you're losing every cycle of vibration. Please note that there are no waves here. It's just an harmonic damped oscillator, okay? This is the other and maybe the most important definition of the Q of a system. Now, please note that if a system is perfectly elastic, delta E is 0 and Q is infinite because you're not losing energy during your oscillation. If you're losing a lot of energy because of it, you have a strong damping, okay, delta E is going to get larger and Q is diminishing. Now, for natural systems, Q is not infinite, of course, but Q for systems that are, if you're not studying a damper for your car, for active suspensions, but for the earth or for the pendulum with which we are measuring time, actually Q is relatively high. Could be 1,000, could be some hundreds, okay? But that's the Q definition. Now, these are the 5 minutes detour about Q. So, for Maria Aurora, we already treated it in some other courses. You have seen the basic definition. Nothing is more basic than that definition, okay? For diploma friends, please, if you simply navigate through the courses and you go to my old wave physics course, so that was active until 1 year ago, in that part, you have a full definition of Q. So for, I don't want to break my whiteboard, but when I was playing my silly trick with the oscillation, with my power adapter there, you can imagine to change the Q. For example, if the pendulum is going to move in a very dense air, Q is getting lower because the damping is larger. Or you can imagine to do with whatever oscillator. If the damping is very strong, you have pretty much no oscillation. All the energy is lost in damping, and Q is getting very low. But for ideal systems where you have no damping, Q is infinite. It's a pure number. So, have I answered to your not question?
Yes.
Yes, yes.
Yes.
Okay, so that is the definition of Q of a system. Okay, now let's try to move on with the lecture. So look at VQ now. 1 over Q is a way to express attenuation. And if mu is equal to mr, this is 0, and Q is going to be infinite, because 1 over Q will be 0. Okay, now, end of a second part of the lecture. SLS, standard linear solid. Now, we can plot two things about that SLS, that are the two quantities that I've shown you in the previous slide. The first quantity is velocity, velocity of something. Okay, now, if you take this expression here, and if you go to omega 0, this part is not entering, and you have the relaxed. What does it mean, omega 0? Long times the relaxed ones. When omega is very high, this is taking the role, and then mu is taking the role. Very short times. What does it mean? That according to the frequency related to the parameters of the system, you have a value at very low frequencies and very high frequencies, a different behavior. Relaxed and unrelaxed. Unrelaxed is here time derivatives. Relaxed is here long periods. And you see that the velocity is not the same. What does it mean? That is dispersion. Because when you have velocity that depends upon frequency, we have dispersion. This is not the dispersion of surface waves, but it's the dispersion due to an elasticity. Now look at the 1 over Q curve. The SLS is providing us something that has pretty much 0, 1 over Q, so Q very high, except here, and this is the peak, and the peak is occurring at the 1 over the square root of the product of the 2 times, where we have a peak of 1 over Q, a peak of absorption. Okay, question. Can we use this for the Earth? Because up to now, we simply built beautiful rheological or viscoelastic networks arriving to the SLS, and SLS is a tool that you can use for many rheological problems, but the question that is coming now, okay, what about the Earth? And these are the final 10 slides. But wait a second. Let me stop sharing, because I want to show to you that the topic of SLS is discussed in many material science problems. And for example, here, as I was showing to you some nice examples of, how to say, animations here, this is an example of the Maxwell model, and you can play some experiments here with a CDF player. There is also another and a beautiful one. Let me see if I have it. Maxwell element, wave. Okay, it should be this one. And you can play also with this. And you have different implementations. The one that we discussed together is this. Oh, you're not seeing my sharing. Wait a second. So you can look at it better. So this is the free CDF player. 3-element viscoelastic models. This piece here of animation is not coming from a seismology course, just to show to you that this is very important for rheology in general. And you can play with this. And you look, stresses T at strain. So you see, changing the parameters here, you can change the parameters. I hope it's not going to explode. You can change those curves. You can change the springs. K1, K2, and that. And if you look at this is stress and strain. This was the old Hooke's law, and you see how it's changing with these parameters. Of course, if you put, I never played, but if you put this at very high values, okay, you are going to get one line. If you put eta at very low values, you get another line. So you can play with these rheological models. But now the final question is it okay, this for the Earth? So my question to you is, what is the Q on average of the Earth? Is it made like that? If yes, okay, we can represent with the sun sinusoid the whole Earth. And now, one of the final messages is this. Okay, let's imagine that we play 2 experiments to measure the Q of the Earth. There are 2 possible approaches. In practice, let's say, we have wave fields and we want to measure the Q of the Earth. So, like in a lab. Okay, the first one, for example, it is to measure Q in time. You stay in a place, a wave field is passing, maybe a free mode is moving, and we got a picture like that, amplitude in time. So the initial amplitude is going to decrease. Now we are standing. It's no more the geometric spreading. Now this is attenuation. So every cycle, we are losing a part of amplitude due to the fact that Q is not infinite. After n cycles, that's the expression. Now, using the definition of Q and this, we can write it like that. And we can write it at long times that the behavior of amplitude in time is described by this. If Q is infinite, A will be constant. Lower is Q, stronger will be the damping. This is called temporal Q. Now let's imagine to make the other experiment. Let's take a picture of a wave field while it's propagating. A picture means that now we are fixing the time and we're measuring how amplitude is losing energy over wavelengths. So it's called the spatial Q. So this is the amount of amplitude that is lost every wavelength. We can integrate this and write it like that. Now there is no time here, but there is space. But here, of course, there is space over velocity. So you can imagine to have, I don't know if you're able to see that, but let's imagine that we have a wave field that is propagating along one direction of the Earth. And if it is arriving here, it has traveled more. We have a sort of the amplitude envelope as a function of space. So these are 2 possible definitions of Q, according if you're staying in one point and measuring a free oscillation to decay, that's the typical experimental value to do. Or if you're taking a vision of a wave field that is propagating and taking a picture in space. Well, if you do it for the Earth, and please note that both of these expressions here are generalizing the expression e to I omega t minus kx, because omega over c is k, of course, well, you get an estimate of the Q of the Earth as a whole, not of a single material, an integral measure of the Q of the Earth. Well, the answer is this. If you take most of the frequencies that are important for global seismology, what does it mean for a frequency that goes to 1 and lower until the free modes of the Earth? Well, if you measure the Q, you have pretty much a constant value. This is the inverse. And let's say if you want to remember it, it's of the order of 100 as the order of magnitude. Then at higher frequencies, well, that's a sort of a mystery. But because we don't know, high frequency, maybe it's different behavior. But let's say that the Q of the Earth as an average is, let's say, just to make the things short 100. It's actually, it's a little bit more, as you can see here. But okay, let's say it's 100, but it's constant. We don't have here, for most of the waves that we can use at a global scale, we don't have a dBi peak as described by the SLS. Okay, taking care about this observation here, what has been suggested is that actually that absorption, not peak but band, can be associated to many different microscopic features, physical features, each of them, for example, defects in the crystal, transverse thermal currents, grain boundary, going to a mineralogical scale, all of this, they can be treated by different SLS. And if we put them together as a sort of a macroscopic view, we can create an absorption band whose Q value typically is 100. Now, second message to take home. And let me make a short pause here before to conclude. I will go quick so we will not lose too much time, but sorry for the Q definition. The second message here. Okay, in the second part of the lecture, we developed rheological models, Maxwell, Kelvin-Voigt, SLS. And okay, it was interesting, very interesting if you want to study polymers or something like that. But for the Earth, we need to take many of them together and to create an absorption band that is actually based on the implementation of every SLS that is taking care of what is occurring microscopically in the rocks. And so, if we consider the Q of the Earth as a whole, it's not infinite, but it's pretty much constant for a large band of values, not at very high frequencies. And we can imagine now an absorption band made by a set of SLS. Is it okay?
Yeah.
Yes.
Okay, final steps. Because now we have a consequence. And let me share the screen again. No, what I'm doing here? No, I want to share screen. Okay. First consequence. Well, it's a sort of a side consequence, but it's important. So now if we want to, and this is coming from your textbook, just to relax it. So now we have a physical dispersion due to an elasticity. And now our system that was a beautiful, in the simplest case, homogeneous, isotropic, not anymore elastic, but viscoelastic medium, now we should ask, what's happening if we put a delta there, like a sort of a green sponge? Well, now we have an additional factor, because we have this attenuation factor operator module, if you want, that is telling us something. And now let's take also the most important consequence of this. Because now you can imagine that higher the frequency is, stronger will be the damping. But why? Because a high frequency wave is going to sample the system much more times than a long period one. And every cycle, part of the energy is removed from it. And so this anelastic, or viscoelastic if you want, operator is damping more high frequencies, as you can see it here, than lower frequency. And that's important. That's a general consequence, especially if Q is constant. But now let's give a look to what is happening to a delta that is propagating into this anelastic medium. Now, if you go to the Fourier domain and if you look at the delta here, at a receiver, the delta that is arriving is not anymore a delta, because this factor here, it's changing it. And it's creating this. It's broadening the delta. And now we have a problem. Because this curve here, part of it is not physically okay. Why? Because if this is a P wave, nothing can propagate in this medium at velocities larger than P waves. And this part of the curve is not nice. It cannot be there. We should relax something in our theory. And to put the things together, so to allow for constant Q, let's say 100, for that operator, the only possibility to put the things in the right order in time, and so to avoid non-causality, is to consider dispersion. And in the 60s, in the 70s, different teams, not only working in seismology, but most of them, they were working in other fields like material science, they suggested what is called the Azimus Law. The Azimus Law is saying, okay, look, if you have a system that is inelastic with a constant Q, you have to insert dispersion. This dispersion is not due to the Q dispersion as before, because Q is constant. But this dispersion is due to the fact that Q is constant and velocity cannot be anymore. Otherwise, we would have part of the signal that is arriving too early. Now, this dispersion is called, as I was telling you, Azimus Law. If you're going to work with an elasticity, you're going to find it. It's a weak dispersion. It's a second order dispersion. But one of the final messages that I want, because the zero message is what's going to appear later, that I want you to take home is that, okay, if our system is maybe very simple, infinite, isotropic, so no boundaries, nothing else, but unelastic, with a constant Q, then it's dispersive. So P and S waves there are tinily dispersed by attenuation, not by boundaries, not like surface waves. And the expression of this Azimus law is based on a reference frequency that usually it's considered to be 1 Hertz. And this was one of the final messages for you to take home, because the very final one, it's a general one, and it's what is going to be reported in the slides. Now, the zero message to take home is this. If we start with a purely elastic medium, okay, an harmonic wave can be described like that. Omega t minus kx. Yes, we know since wave physics. And omega and k are related by velocity, of course. Omega over k is velocity. Well, we can imagine that we can replace velocities, the elastic ones, with complex ones, where the real part is still related to the elastic one, but the imaginary part is related to the q. And usually this is called slowness, because you see it's 1 over velocity, so it's called slowness. And it has a real part and an imaginary part that is related to q. Wait a second, if q is infinite, that is going to be 0, and we're going back to the good old elastic word. But if it is not, if q is not infinite, and if we have an elasticity, as we discussed during this lecture, you can imagine that C is becoming complex, K is becoming complex, and the real part is the one related to the propagation as usual, but we have a damping part here that is taking care about the attenuation in space or in time. If Q is infinite, again, it's going to be 0. If it is not, well, you have this that is damping, especially the high frequency part. And velocity, if Q is constant, has to be timely dispersed following the Azimus law. This is the message 0 to take home. And actually, what you can imagine is that all the velocities that you studied, like beta, like alpha, or phase and group velocity of surface waves, now it's becoming complex with the real part and an imaginary part. In jargon, usually you take 1 over slowness. The real part is this part, so the real part of the slowness is related to real velocity, and this quantity here is called attenuation. It's called, in jargon, phase attenuation, and it's related to Q. Okay, this was the zero message. Let me show to you just the concluding, not cosmetic, but let's say more aesthetic slides. What about Q for different materials, not for the Earth as a whole? Well, it depends by the rock type. For example, the outer core that is pretty much an ideal fluid, well, it has no QS because there is no definition there, because there are no S waves. And Q of P is very high, typical of fluids, of ideal fluids. Okay, metal materials, you see very high values. Granite, very high values. You can reach relatively low values just in sedimentary materials like these ones. And it depends also on the presence of fluids, of course. But still, it's of the order of tens. So the Q effects are relatively tiny, but they are there. And what to do with Q? Well, of course, you can do tomography of Q, because attenuation, now not looking at the Q value as a global measured on the surface, but measured for different materials, you can relate it, for example, to profiles, and you can do tomography also with Q. This picture is coming here, is coming from your textbook. And one of the final consequences about Q and damping and then elasticity is also related to hazard. Because, for example, you see here 2 seismograms that have been recorded from a source, but one is recorded at the same distance, but one is recorded in Nevada, so, okay, let's say on the West Coast. The other one is recorded in Missouri, so central eastern US. And look at the totally different, how to say, not behavior, but appearance. Look how here the amplitudes are lower and the high frequencies have been lost. They have been damped compared to this one. And actually, and this is what I was mentioning during the last lecture, if you compare now what is called in the seismic hazard jargon, attenuation relationship, I don't like that name, but you can call GMPE, ground motion prediction equation, or whatever. If you plot the peak of the amplitude of the ground motion versus distance, recalling what Charles Richter did, versus distance for Eastern US and Western US, you see that the behavior is totally different. Magnitude 7, this and this, magnitude 6. You see, the effect of the damping is almost the effect of 1, not degree, because it's not degree, 1 unit in magnitude. That means a huge energy more, but it's going to be dissipated more. And that's why when you take a seismic hazard map for the New Madrid zone, and this is recalling what we discussed during the last lecture, compared to the Landers one, wow, the hotspots that are left on the ground are totally different. Look at how broad they are in this case. Now, sorry, as usual, I was going a little bit late, but let me, so again, just to follow the logic, let's give a look again to what we discussed at the beginning, and let me maybe share again for 1 second the slide here. So in the recap part, we discussed the solids, usually known, the fluids, Newtonian fluids, usually known, but then we mix them. We consider the creep and stress relaxation experiments for some rheological circuits, Maxwell, Kelvin Voigt, SLS. Well, we have not computed this. And we found the relaxed and unrelaxed modulus. Then we consider the Q. I would suppose it was in your pocket, but okay, we discussed it. It's coming from the definition the very simple definition of a harmonic damped oscillator. You can imagine it it's used to compare the inertial force that is in omega 0 over the damping that is in gamma. It's a pure number. If omega 0 is winning, then you have very large values of Q. If gamma is winning, you have very low values for Q. Going to the Earth, we consider the time Q, the spatial in time and in space, and we have a vision that Q, on average, for the Earth is about 100, and it's constant. With constant Q, in a viscoelastic model, we have to take care about causality, and that's giving us dispersion intrinsic dispersion due to attenuation, if Q is constant. And then that in general, what we were considering as real velocities, well, they have an imaginary part that is taking care about the damping in space and time. And that's the effect. But Q on average, but also for many materials in the Earth, is quite large. But it's not infinite. So an elasticity, its effect on high frequency waves that is more pronounced, and consequences for tomography and hazard. So that's also the recap of this. I hope, I know. In this course, I'm trying to squeeze too many things. But with Karim, we discussed a long time ago that it's also the place also to put some concepts that you're going to use also in other courses, so that you have some basic theory for them. For example, today we have also discovered that an SLS can be used to describe the reaction of systems on short time scales and on long time scales. Now you can use that also to imagine the rheological behavior of a rock on 1 million of years. Short time scales, seismic waves. Long time scales, fluid dynamics. And so on. Now I have so sorry if we squeezed in 1 hour and a half these concepts, but can be expanded a lot. And I'm going to ask you a homework, and it's a real one this time. Well, I will never check you, but I'm going to ask you at the exam. So it's better if you solve it. Now, the homework is simple, and if you're good, it's going to take 5 minutes. And hint, the answer is on many textbooks, for example, also on Stein and West session. Okay, let me share for the last minute my screen here. Look at this slide here. You see that QP, defined for P waves, and S for S waves, QP is larger than QS with different ratios. Okay? Well, I want you, and that's my question, to tell me what is, on average, the ratio of QP over QS. It's a ratio of 2 integers, don't worry. So it's easy. So general problem, what is QP, what is QS? Why QP is larger than QS? How much it is in average, on average. It's simple. If you want, I tell you. Well, it's 9/4, I hope. But I want you to discover why. If you look at the proper page on your textbook, it takes 2 minutes just to read it, because it's there. Okay?
Well, cool. Can I say something for that?
Sure.
Well, the VP value is not the root square of it has the model, the elastic model, that is the mu plus.
No. Wait a second. Wait a second. If you stay in an elastic, purely elastic world, VP is square root of lambda plus 2 mu over rho, and QP and QS are infinite.
All right.
In the elastic world, Q is beautiful, infinite. But in the real world, QP and QS are very high, let's say 200 and 100, so very high. Takes time to damp it. A Q of 100, it's a high Q, okay? Because Q is also the measure on how long the amplitude is getting of 1 over E. With 100, you have to wait. Your pendulum is going to move for a long time, okay? Now my question is different. In the non-elastic world, QP and QS are not infinite. And the ratio using theory is 9/4. So I told you, but you have to read why. Is it clear? Why 9/4?
Okay.
Yes.
Okay.
The answer is not blowing in the wind, is written on many textbooks, included Steinway session, in the proper page. You know, my homework is simply to tell you, read those pages and find the answer. Okay?
Yes. Okay. Okay.
Okay. See you on WED, and we're going to discuss something totally different, except one thing. We're going to speak about fluids under gravity.
Oh, okay.
Just also in that case, we're going to speak about tsunamis, and I will try to squeeze in 1.5 hours a course of 10 hours. Okay? Just
Okay.
again, as usual, just use logic. Okay? Okay, we did it also with 15 minutes of delay. Okay, please, goodbye and have a nice start of this week. I know it was terrible, but now you can discuss about rheology. Good news.
Yeah.